Today we're going to be going over the review for our acid-base test, and you can reference back the notes throughout your review if you choose to do so. We're going to start with our definitions. First of all, we have molarity, and molarity is just a way of saying the concentration of your solution. And the way that we calculate molarity is going to be in moles per liter, moles over liters. And if you have a dilute solution or a diluted solution, it means that you have a small amount of solute present. Remember, solute is the thing that's being dissolved, so small amount of your substance dissolved. If you have a concentrated solution, it's the opposite. You have a large amount of solute that's dissolved in your solution. And it's all relative. When you talk about having a titration, titration, remember, is a way that you can find the unknown concentration of a solution of either an acid or a base. We can abbreviate there. Normally we're trying to find the concentration of an acid, but we can use the burette, and we can use another solution that we do know the concentration of, and you're trying to find the equivalence point or the end point. And that's going to occur whenever the amount of hydrogen and hydroxide concentrations are equal to one another. If you remember right, when we talked about the pH scale, that this will occur when the pH value is equal to 7, and we have what's called a neutral solution. And one of the things that we can use to determine when a solution will reach its endpoint during a titration is an indicator. And an indicator can be anything that changes color to indicate the pH value, or whether it's acidic or basic. And sometimes you can get a wide range of different values, or sometimes, like with our phenolphthalein, it's either just clear or pink. And those are our only two choices. And finally, we have salt. Remember, salt is not just an ACl, it's going to be any ionic compound, and it will be a product of an acid-base reaction. You can create them in other ways as well, but you'll always, one of the products of an acid-base reaction will always be a salt. And you can just put Rx in for reaction. Okay, let's talk some more about indicators. We used pH paper, but we also have our litmus paper and our phenolphthalein. So let's make a little chart over here on the side. We're going to have two rows here, one for acid, one for base. And then we're going to have two columns. We're going to have one to talk about litmus paper, and then we're going to have one to talk about phenolphthalein. We can abbreviate there. Now, if you have an acid and you put litmus paper into that, it doesn't matter if it's red litmus paper or blue litmus paper starting out. When it's put in with acid, you will get a red color at the end. If it's red, it stays red. If it's blue, it'll turn red. If you have a base and you put litmus paper in it, it will be blue. And again, that's easy to remember, base, blue. Phenolphthalein is that clear, colorless solution that we started out with, and that whenever we add it to an acid, it stays clear and colorless. Remember, we can't just use the word clear because clear just means you can see through it. Colorless means it lacks pigment, it lacks color. And when we add phenolphthalein to a base, we get that nice hot pink or magenta color. So it's very obvious when you add phenolphthalein whether you're dealing with an acid or a base. And then, of course, we also have the pH paper that had a wide range of colors you saw on the side of your vial there. You also need to review your other characteristics of acids and bases. Those are in your notes, and those are going to be on page 335. So things like which one reacts with a metal to make hydrogen gas, which ones taste sour, which ones taste bitter, things of that nature. Now we have some problems that we're going to look at. The first one says a solution has a volume of 275 milliliters and contains 7.55 grams of potassium permanganate. What is the molarity of the solution? So you have to remember how we calculate molarity. Molarity is equal to moles divided by liters. And you'll notice if we look at our numbers given that we don't have either of those things. We have milliliters and grams. So you have to first change our 7.55 grams into moles by using the atomic mass value from the periodic table. If you take the number of grams of your substance and divide by the molar mass value for that compound, then that will be the same as dealing with the number of moles. So we go and we look up potassium. Potassium has a value of 39.10. Then we need to look up manganese, Mn. It's got a mass of 54.94. And then we need to look up oxygen, 16, but it's 16 times 4, which is going to be 64. And we add those values up, and we end up with 158.04, and that's grams per mole. So whenever we divide by that, our gram units are going to cancel out, and we'll be left with just the number of moles on the top, which is what we need. And we have to divide by the number of liters. You have to remember that 1 liter is equal to 1,000 milliliters. So if we have 275 milliliters, a quick way of changing that is to take our decimal and move it back 1, 2, 3 places. So this is the same thing as 0.275 liters. So that's what we're going to divide by. And when we take a look at our units and see what cancels, grams is the only thing that cancels out. And when you type that in your calculator, you're going to push 7.55 divided by 158.04 divided by 0.275. And we end up with an answer if we round it to 3 significant places, because our smallest one has 3 sig figs. We get 0.174, and since it's moles over liters, remember that's going to be the same thing as our capital M that's underlined, and that's going to be of KMnO4. So the way you would read that is 0.174 molar potassium permanganate. Okay. For the next section, we have some naming of acids and bases, and on your test, I will give you a reference sheet that you can look at for especially the acids, knowing all the special rules for those and the exceptions. When you first look at these, naming the bases is probably the easiest thing, so you look for that, and you know that it's a base whenever it ends with OH, except for acetic acid. Acetic acid is a weird one, remember. So we have Ba, which is going to be barium. And then when you have OH, that's our polyatomic ion hydroxide. The only time you'll see anything different is if it's a metal that we don't know a certain charge for. So for example, if you had cobalt and it was OH2, just like the other one. Cobalt is a transition metal. It has an unknown charge. It has varying charges it can take on. So whenever we name that, we would have to put a 2 in Roman numerals following the name, and then just follow with hydroxide. The rest of these are going to be acids, and we know that because they all start with hydrogen. And then remember, there are different rules for if there's oxygen or not, and if there is oxygen, it depends on how many oxygens there are. So if you look at your notes where it has your list for how to name these, when we look at this first one, there's two oxygens at the end. So you go where it says two oxygens, and it tells us there's no prefix, and our suffix will be OUS. So you look at the element in the middle here, chlorine, for the root. So we know it starts with chlor, and then since it has only two oxygens, we're going to end it with OUS, and then acid, chlorous acid. The next one has no oxygens at all. So when there are no oxygens, that's when we get that prefix of hydro. Then we need our root for fluorine, which is fluor, our suffix ic, acid. This next one is going to be one of our exceptions. Remember, when there's sulfur or phosphorus in it with some oxygens, that's not going to be on a list that you can just look it up because it doesn't quite follow the rules. So this one is going to be sulfurous acid. H2SO4 would be sulfuric acid. Okay, again, we've got a situation where there's no oxygen, so we start with the prefix hydro. And then remember the root for sulfur is just sulfur. Then ic, acid, hydrosulfuric acid. HBrO4, when there's four oxygens, we're going to have a prefix of per. Then we look at our element in the middle for our root, brome, from bromine. Our suffix of ic, acid. HiO3, when there's three oxygens, there's no prefix. We just start with the root for iodine, which is iode. Then our suffix ic, acid. Just look it up on the list on how to do these. Then finally, we have a situation where we have only one oxygen. That's where we get hypo for low. Then we need our root for the chlor, in the middle, chlor. And then OUS is our suffix in this case, acid. If we're going to go the other way and come up with some formulas from the names, ammonia is one of our exceptions. Remember, ammonia is a base, but it does not end with OH. It's going to be NH3. And there's another exception I want to add on here. Our weird one for acids is acetic acid, or vinegar. And of course, that's kind of repetitious to put that there, but we have our formula for that, which is CH3COOH. And remember, it's that H at the end that can be pulled off and donated. That's our definition of acids, is it has a proton or a hydrogen it can donate. If we have copper with a 2 hydroxide, that means our charge on the copper is +2. We know hydroxide's -1. So when we write our formula, since we have to have 2 hydroxides to balance out the charges, it goes in parentheses and our subscript goes out front. Okay, for the last one we have what looks like periodic acid, but the way you would say it is per and then iodic acid. And whenever you have a prefix of per, remember per means you're going to have 4 oxygens at the end. So we know it's going to end with O4. And it's an acid, so acid means it's going to start with hydrogen. And then we look at our root in the middle. Iodic means we're going to have iodine. So HiO4 is periodic acid. Okay, for the next section, we're going to find the pH value. So this first column, we're going to write the pH number, and then in the last column, we'll figure out, is it an acid, a base, or is it going to be neutral? So the first one, we have a hydrogen ion concentration, or H+, of 1 × 10⁻³ . So if this is an H, and we're trying to find pH, remember, as long as this value at the beginning is 1, we can just look at our exponent and take the negative sign off of it. So our pH value then would be a 3. When pH is less than 7, that means you're dealing with an acid or an acidic solution. If you have a hydroxide ion concentration or an OH value, and we're trying to find pH, you have to first figure out what POH would be and then do a little bit of math. The POH would be 5, just that with the negative taken off. And you have to remember the fact that pH plus POH is equal to the number 14. So if POH is going to be 5, then our pH has to be 9, because 9 plus 5 is 14. And if the pH value is 9, that means that it is greater than 7. And whenever you have a pH value greater than 7, that means you have a basic solution or base on your hands. Okay, the next one we have is pOH value of 11.0. Remember, pOH plus pH is going to give us 14. So 11 plus 3. And we already had a pH value of 3, and we already said that is going to be an acid. And then finally, we have a hydrogen ion concentration of 1 times 10 to the negative 7th. So our pH value is just our exponent with the negative removed. And whenever it is equal to 7, that's whenever we have a neutral solution. Okay, so you should be prepared to find any of those values given one of them. You should be able to find the other 3, just like we did in the chart on the homework. Okay, the next thing you have to do is be able to complete neutralization reactions. Remember, neutralization reaction is just another way of saying acid-base reaction. And whenever you have one of these, you're going to make 2 products. You're going to make a salt and water. So a metal and a nonmetal will come together to make your salt right there. So the first thing you want to do is figure out what's your acid, what's your base, and why. So NaOH is your base because it has OH, hydroxide. This is your acid because it has an H, or hydrogen. You have to make sure you have equal amounts of those. If you have more of one than the other, you have to make them match before you continue. Since we only have one of each, we can go ahead and finish this. The other 2 parts are what's going to come together to form your salt, and you always write the metal first. The metal is to the left of the staircase on the periodic table, and that's going to be sodium in this case. So we have NaIO4, and then the H and the OH will come together to form one water. And that's it. So try again on the next one. We've got H2SO4, sulfuric acid, because the H. And then we have lithium hydroxide, a base, because the OH. We have 2 hydrogens and only 1 OH, so to balance that out, we're going to put a 2 in front of the lithium hydroxide. At that point, you can go ahead and balance these other 2. The metal that's paired with your hydroxide will go first, so we have 2 lithiums paired up with your sulfate. And since we have 2 hydrogens and 2 hydroxides, we're going to have 2 waters form along with that. Okay, on the next one we have phosphorus acid with 3 hydrogens combining with potassium hydroxide, our base, with only 1 hydroxide. So you've got to make those match, so we need to put a 3 in front of the KOH. The PO3 and our 3 potassiums can pair up. The potassium gets written first because it's our metal. And since you have 3 hydrogens and 3 hydroxides, you also have 3 waters formed. Okay, for the last neutralization reaction, we've got aluminum hydroxide with 3 hydroxides on our base. And we have hydrosulfuric acid with 2 hydrogens. Anytime you have 2 and 3, what number do you need to get? 6. So if we have 3 hydroxides, to make us have 6 of them, we need to multiply it by 2. If we have 2 hydrogens, to make that be 6, we need to multiply by 3. Then we can make our metal and nonmetal pair up and form our salt. So we'll have 2 aluminums combining with 3 sulfurs. Remember, this 3 gets distributed to both of those substances. So we'll have our 2 aluminums first with our 3 sulfurs. And then since we have 6 hydroxides and 6 hydrogens, we will form 6 waters. And those are your neutralization reactions. Okay, for our very last problem, we have one of our M1V1 equals M2V2 problems. and we have it in the form of a titration problem. We have 22 milliliters of a 2.0 molar solution of barium hydroxide required to completely neutralize 35 milliliters of an unknown solution of phosphoric acid. And we want to know what is the molarity of the acid. So we're going to start with our equation, M1V1 equals M2V2. And we're going to figure out what we have and what we're trying to find out. In this case, we're not diluting anything, so it really doesn't matter which one is 1 and which one is 2. You just have to be sure that the ones that are talking about the same substance are paired up. And a very clear way of knowing when that happens is going to be this word of. If you have 22 milliliters of a 2.0 molar solution, both of those are talking about the same thing, and so you can make that be V1, sorry, that's our volume, and then this would be M1. They're both the same substance. And then you know that the other thing, in this case the acid, that would be our second volume, and the molarity M2 is what we're trying to find out. So we have to rewrite our equation to solve for M2. So since these two guys are multiplying right here, the way we undo that is to divide by V2. And if it's helpful for you to go ahead and plug in your numbers and then do the algebra, you can work it that way as well. But whenever the V2 cancels out, then to solve for M2, it's just M1V1 divided by V2. So our first molarity is 2.0 molar times the 22 milliliters. And remember, you can leave it as milliliters as long as both units have the same, or both volumes have the same unit. So our second volume will be 35 milliliters. So those units will cancel. And in your calculator, you just have 2 times 22, which would be 44, divided by 35. And if we round it to 2 significant digits, like everything else that's on our page here, we end up with 1.3. And our units then will be this capital M underlined for molar. And it's phosphoric acid. So that's H3PO4. And that is the strength of that acid that was unknown. Your test is going to be on Wednesday. Test on Wednesday. I expect you to be familiar with these topics on the review, as well as the other characteristics of acids and bases. You need to look in your notes on page 335, like I said earlier. Okay, thank you very much.